Okay, so that's the last speaker of today, from the thematic section, and the last speaker is Pedro Salomão from University of São Paulo, IME, University of São Paulo, and he did a PhD, actually the master and PhD at the University of São Paulo, under the supervision of Clodoaldo Ragazzo. And if not mistaken, I saw your lattice, you have a undergraduation in mechatronic engineering and also in public administration, right? Public administration.
Yeah, that's
okay,
true.
Great. So it's a very eclectic formation. And he also have, he did his PhD in 1996 and has many distinctions, including the Sociedade Brasileira de Matemática Prize, the Simons Visiting Professor, and also the Bessel Research Award from the Humboldt Foundation in Germany, I think, and has been very prolific with many publications, including Duke and Invenciones. And today, Pedro is going to talk about transverse foliations in the Euler problem of two fixed centers. Pedro, please.
So, thank you, Daniel, for the introduction. I also thank the organizers for the invitation. And so I'm going to talk about this. Something is not working here, but I can use this scroll. The Euler problem of two centers in the plane. So this is the problem of studying the motion of a particle that's attracted by two centers. And these two centers, they stay at these points in the plane, like this -1, 0 and 1, 0. And the law of attraction is the usual law of gravitation given by Newton. So the motion of this particle, which sometimes we call, so this is the satellite, and here the centers are sometimes called the primaries. So the motion is described by a Hamiltonian system. We give a Hamiltonian function, which is this function h here, and it depends on the position x and y, and the momenta px and py. And the Hamiltonian that describes the motion of this particle is given by this expression here, where we have the Hamiltonian given by the potential and the kinetic part, which is given by this expression. Then we just have to integrate the Hamilton's equation associated to this Hamiltonian function, which is given by x dot is equal to d h d px dot, and is equal to minus dh x, and the same for y. And so we have a four-dimensional first order equations, and if we integrate these equations, it's autonomous. We have a flow, and this flow preserves the Hamiltonian function h, which is the total energy of the particle. And it depends on this parameter mu, which is called the mass ratio, which is so the mass here and in this center is mu, and at this center here is 1 minus mu. So the total mass is normalized to be equal to 1, but the system doesn't have symmetry enough to eliminate this parameter. So this parameter is still there. And sometimes people they model the motion of an electron near two protons, and the mass ratio, it will depend on the number of protons at each center. So this problem is called the Euler problem because it was studied by Euler. There's a very nice publication by Euler in 1760. And at that time, Euler also noticed that the system is not so complicated, meaning that there is another integral of motion for the flow, which is given by this expression that we see here. So G is a function, it's a real valued function that is preserved by the flow, and it's independent of the Hamiltonian. So,
so these two masses are fixed, and you have a probe mass that is moving.
Yeah, we study the motion of this particle here, of this mass at this point here. So we have this other integral of motion given by the function g. And so the system is a flow on a four-dimensional space, and it preserves the energy, h. So in general, what we do is we fix the value of the energy, and we study the dynamics restricted to that energy level, which is a three-dimensional manifold in general. And given this other integral of motion, it turns that the system here is totally integrable. And if we look at this three-dimensional energy level, we're going to see a lot of invariant time. So the flow is not really too much complicated, but as I will explain later, it's very important for this type of objects that we study here to consider integrable Hamiltonian systems. So as I said in the beginning, the flow preserves the energy of the particle. So if the energy is small, so this is the plane, and with coordinates x and y. And if we project the motion of the particle with low energy, what we're going to see is that it stays close to the primaries. It cannot go too far unless it gets extremely far in an unbounded region, but I will disconsider this situation. So the important dynamics lies near the primary. If you increase the energy, then what happens is that the energy level, it gets, so for low energy, you have two components of the energy level, which projects in these two regions close to the primaries. If you increase the energy, these two components, they get connected as a connected sum, and what we see is just one connected component of the energy level. And when we project this three-dimensional energy level, what we see is this region, that these two smaller regions about the primaries, they get connected. And here, now we see trajectories that go from one side to the other. So here, we only see these trajectories that we call satellites. But for higher energies, meaning energy above the critical value, which is given by this value that depends on the mass ratio, these components get connected. And then we start to see trajectories that go from one side to the other. These trajectories are called lemniscates. And if we increase a little bit more the energy, as I will show later, what we start to see is that, so here are the primaries, we start to see some trajectories that move like that. They do not touch the interval in between the two primaries, and these trajectories are called planets. Okay. So more or less, if you and there is this value of energy which is equal to 0. If you go above this energy, the typical trajectory is unbounded. So the dynamics is not really interesting. So today I will talk more about what's happening with the dynamics above this critical value, which is a negative value here, and in between this critical value and 0. So this is where the dynamics gets a bit more complicated. Okay, where you have this transit trajectories, the lemniscates and the planets. So why studying this system? So there are a lot of systems that are modeled like this one, for instance, a Hamiltonian, given by this expression that we see here. The 2 degrees of freedom Hamiltonian system. And I put here a list of such Hamiltonians, that the expression of the Hamiltonians are quite similar, but the dynamics might be extremely different in some ways. For instance, I put here these two in blue, the rotating Kepler problem, the harmonic oscillator, in this list of 5 other problems. The rotating Kepler problem, we still see the kinetic part. We see that it also has this term here, which is due to a rotating system, and the potential is very simple. So these two systems are also integral, and in some sense they are much simpler than the Euler problem of two centers. And these other three systems here, they are not integral. Maybe they are extremely difficult. The dynamics is more or less it's bad, but maybe it's easier to study this High system here. Dynamics is a bit easier, but it's still non-integrable. It's still very complicated to describe the dynamics. And maybe this is the easiest one among these three Hamiltonians. The second is the Hughes lunar problem. And the most difficult one is this guy here, the circular planar restricted three-body problem, which describes the motion of a particle or a satellite near two bodies, but now they are not fixed. They rotate along a circular trajectories about the center of mass. So this is by far the most difficult problem, and somehow the Euler problem of two centers is a simplification of the circular planar restricted three-body problem. And the Hughes lunar problem is also another type of simplification of the first one. And the High system is a different dynamics of a star in a galaxy. Okay, they are all this list of Hamiltonians, the dynamics, they might be extremely different, but as I will show today here, I'll try to explain today here, they have a lot of similarities as from a global perspective. So what do I mean with that? First of all of the systems, so they are autonomous Hamiltonians. So we have a flow on a three-dimensional manifold. It might be very complicated, but this flow on these energy surfaces, they all share, first of all, the same property. They are all flows, like Chodensky flows. So a Hebb flow, it's possible to define a Hebb flow in a more intrinsic way. You have a three-manifold, and suppose that you have a contact form on this three-manifold, and a contact form is just a one-form lambda that satisfies this wedge product is a three-form that never vanished, so it's a volume form. And so this contact form produces a vector field given by these two equations. These two equations determine a vector field on this three-manifold, and this vector field, for the case that I mentioned before, for those problems, the associated contact form, it produces a vector field that's parallel to the Hamiltonian vector field. So the dynamics is the same. It's just a reparametrization in time. Okay, so so all of those systems we can study using the formalism of Hebb flows. Okay, and the object that I will talk about today is the transverse foliation. So we have a three-dimensional flow. Sorry. So what is a transverse foliation? It will be a foliation of this three-dimensional manifold, but it's a singular foliation. And this foliation is adapted to the flow. So the singular set of this foliation is formed by finitely many periodic orbits. So you have finitely many periodic orbits of the flow. And in the complement of these periodic orbits, you have a foliation by surfaces. And the surfaces are in fact punctured surfaces. And at each puncture of the surface, it converges to one of these periodic orbits of the singular set. So I gave here, it's just a picture of an example of a Hebb that I show the singular set here has two periodic orbits, P3 and P2. These numbers 3 and 2 are related to the indices of these orbits. And we see a family of surfaces bounded by these two periodic orbits. And these surfaces are assumed to be transverse to the flow. They have the vector field is transverse to the flow. So in this case, we have this red periodic orbit that we see here. This is like a section of the foliation that we see on the left. And on the right, I tried to describe this three-dimensional foliation. And inside, so we have this 3VO0, which is a periodic orbit, and we have two planes bounded by this periodic orbit. And inside this two sphere, we have this index 3 periodic orbit, which is concentric, and a family of planes. This family of planes is foliating the interior, but as a one parameter family of disks. But we see also here that there is a cylinder connecting the red orbit, the boundary of this three-ball, let's say, to the periodic orbit in the interior. So this gives a very simple example of a transverse foliation that could appear or adapted to a flow. But this is what the main idea of what I'm going to talk about is to show exactly that for most of those systems that we saw there, here, so they admit that type of foliation. Although the dynamics could be extremely difficult or extremely complicated, it is possible to show that the dynamics admits this type of transverse foliation, which gives us a good idea of what's happening with the flow for those systems, even if the underlying dynamics that we see between the leaves here, which is transverse to this foliation here, it might be very complicated. So, so this is more or less what I wanted to say. Why transverse foliation? So we have a non-integrable Hamiltonian system. The flow might be, when you fix the energy level, extremely complicated. But if you produce a transverse foliation, somehow you have a very good picture of the paths of the flow inside the energy level. So even if you have like some chaotic motion, you see under this the existence of these foliations, you see some order inside these schemes. And moreover, because we have these foliations, we might study the transition maps between leaves in this foliation, and this could give us some information about the dynamics. For instance, so Poincaré used this type of foliation. In fact, it was a global surface of section. It's the simplest example of such a foliation to prove, for instance, the existence of infinitely many periodic orbits in the three-body problem. The first system that I saw in the I put in that's this system here that Poincaré proved using a global surface of section. For more general transverse foliations, it's still possible to obtain, for instance, results about the existence and multiplicity of periodic orbits. And also you can create a symbolic dynamics associated to these leaves. For instance, you take a trajectory that it intersects some of the leaves, and you put some symbols on these leaves, and then you try to describe the whole dynamics using the symbolic dynamics associated to this transverse foliations. And in celestial mechanics, which are systems of this type here, they are interested in these transit trajectories. For instance, in the three-body problem, they use the system here to design space missions. And for instance, you would like to send a satellite from the Earth, which is one of the primaries, to the moon, which is another primary, and you want to find using this gravitational forces, you want to find a trajectory to go from one, near one of the primes to the other, and then you need to study the dynamics associated to these transit trajectories, the one that I just put here, the ones that are crossing this neck region in the energy level, and also, for instance, you may wish to study the homoclinics associated to the Lyapunov orbit that I will mention here. So the method to study the existence of this transverse foliation is solving a PDE. Okay? So there is this PDE, which we call a pseudolomorphic curve. This is just this mapping here from a surface to, instead of mapping to the three-manifold M, we take to the symplectization of this three-manifold. So this is just R cross M, the three-manifold, and this is a four-dimensional manifold, and we can construct an almost, it becomes not a complex manifold, but an almost complex manifold for a suitable J. And then we try to solve this equation, which is essentially, this equation is del bar equal to 0. This is just a holomorphic map. But now, instead of considering a complex structure, you consider an almost complex structure. So it's a map from a surface, which in those cases that we saw before is just planes and cylinders, to this symplectization, but later we project from the symplectization to the three-manifold. And the projection to the three-manifold will be what we see here. Okay? Will be the surface that we see associated to adapted to the flow. So that's the main idea. We constructed those transverse foliations solving this PDE. And there is a notion of energy for this surface, this pseudolomorphic curves, and when the energy of this surface is finite, the point is that when it's finite, these holomorphic curves, they approach the periodic orbits. So as in this picture here. So we have cylinders and we have planes approaching these two periodic orbits, and that's what happens in general when you have a pseudolomorphic curve with finite energy. Doesn't matter so much how you compute this energy, but there is this notion of energy called Hofer's energy. When it's finite, the surface approach this map. When you project to the three-manifold, it approaches the periodic orbits. Okay, so that's how we construct those transverse foliations, solving a PDE. And now here it becomes the motivation to study the Euler problem of two centers, because that system is integral. Okay? So to find a pseudolomorphic curve, it's extremely difficult. It's like solve any other PDE. In general, it's very hard. So the main idea here to solve a PDE like that is the following: we start with a system which has a lot of symmetry, and that you try to solve more or less explicitly those PDEs. Okay, and in the particular case of a pseudolomorphic curve, the symmetry fits well when the system is integral. So in most of the cases that we can construct pseudolomorphic curves to solve our nonlinear system, we start with an integrable system, we solve it, and then there is a deformation. The point is that these pseudolomorphic curves, they do not appear alone. When you find one in general, you find there is a family of such pseudolomorphic curves nearby, forming like a manifold, a local, finite dimensional manifold near that curve. So in the case of these foliations here, we have these blue curves, the blue planes that we see here, and they form one parameter family of such curves near that given one. So, and the red one is what is a zero-dimensional manifold. It's an isolated, and also the green is an isolated curve, and we call them rigid curves. So like this. So here we see three rigid curves, like the two hemispheres of those. That's the true sphere and the cylinder connecting those two periodic orbits. So this and also you can deform the data that you have of your problem from one Hamiltonian system to the other, and this and you have a deformation of such curves. You try to push from a situation where the system is integral to a situation where it's not integral. That's the main reason why we study the Euler problem of two centers, because all of these examples that I showed in the beginning, they are especially those which are not integral, they might admit, and for some of them we can also prove this, a foliation which is very similar to the foliation that we see in the Euler problem, although the dynamics might be completely different, but the foliation adapted to the flow is the same, especially when we cross the energy level. We are slightly above the critical energy level. So that's the main reason we consider the Euler problem. So let me try to explain how we obtain these holomorphic curves in the Euler problem, and then maybe I can mention something about the existence of these foliations for the other systems. So we have the plane X with coordinates and X, Y, and Y. So the system is integrable. And what in general we do is there are suitable coordinates. Instead of considering X and Y, we change for U and V, or where the relation is given by these these expressions here. They are called elliptic coordinates. And there is also a change of coordinates in the momenta given by this expression here. And this change of coordinates is symplectic, so it preserves the Hamiltonian form of the equations. And the new Hamiltonian system in these coordinates is given by this expression here. Okay, so this is the new Hamiltonian, which decouples. Now you can see as the sum of two Hamiltonians. Here, let's say K1, and here another K2, which are Hamiltonians of 1 degree of freedom. So it's much simpler when you use these coordinates. The Hamiltonian decouples, and so you have two systems that work independently of each other. That describes completely the dynamics. And this system of coordinates, not only it gives a nice form for the equations, but it also regularizes collisions. I didn't mention in the beginning, but we have the primaries here, -1 and 1, and some of the trajectories, they collide. So when they collide, it's a so the flow is it's not a complete flow, so it collides in finite time. So when you change coordinates, you don't see these collisions anymore. So it's a regularization of the collisions. And for the original flow, what we see is that the trajectories, they bounce back as if they were hitting the primary and going back. So that's when you look at the trajectory in this system here. When you cross a certain point which corresponds to the collision, so this trajectory, what you're going to see is just a trajectory that bounces back. Something like that. So as I said in the beginning, we have this parameter mu, which is in between 0 and 1, which is the mass ratio. We have to consider it. So let's suppose that we fix the mass ratio, and what's happening when we change the energy. And when we change the energy, let's say we have the low energy when we have two components, it doesn't matter so much. And so we have this range of energy here, which I call high energy, which is from this point to 0, and above 0, which is the case of unbounded trajectories that we are not interested in this case, so I will just ignore. But for high energies, we have 3 interval of energies. It's not so high, it's a middle high and really high. I will call these 3 intervals that we see here. 3 intervals of energy for fixed mass ratio. So the dynamics changes when you cross, when you are in each one of these intervals here, and the transverse foliation that we see in the energy level may also change. So in this case, let me just mention that we are studying after regularization, after using elliptic coordinates, the energy level. It's something which is diffeomorphic to S1 cross S2. Okay, so this is the component of the energy level. It's compact, and we are studying the dynamics that lies in this component of the energy level, which is an S1 cross S2. Okay, and this mapping here, it's a 2-to-1 mapping. It's a double covering, and it sends some circles to the collision points. It doesn't matter so much, but after regularization, we have this S1 cross S2. So this is the component that matters for us. So I will present this result with Nayara De Paulo, Humberto Rinievich, and Shanshong Kim, which says that for every mass ratio and every energy between this critical value and 0, this component of the regularized energy level admits a transverse foliation, which is the projection of a finite energy foliation in the syncretization. So to explain a little bit more of this, what's happening with this foliation. So this foliation has a singular set, and this singular set has 3 periodic orbits. So these 3 periodic orbits, they are what we call the exterior collision orbits. Exterior collision orbits. So, okay. And both of them. So it's an orbit that when you regularize, this collision orbit becomes a periodic orbit. It bounces back, and so it becomes periodic after regularization. And in this neck region, there is what is called the Lyapunov orbit. So which is a hyperbolic orbit that lies in this neck region here. It just oscillates here. Okay? Back and forth. So the singular set is formed by these 3 periodic orbits, and the foliation is, a foliation that looks very much like the one that I showed in the beginning, like formed by planes and cylinders connecting those periodic orbits. And I will describe them here. So the dynamics, what we see here is the dynamics of K1 and here of K2. The Hamiltonian is decoupled, so we have these 2 planes, UPU and VPV, where the dynamics is integral. And the foliation that we see for in this 3-dimensional energy level. So this is it's very simple. In fact, it's S1 cross S2. So this outer circle corresponds to a 2 sphere, and the inner circle is another 2 sphere, which is identified with the outer one. So, and this is the S1 direction when you identify this two spheres. And So what we see in this component is that we have the Lyapunov orbit, which is the hyperbolic orbit with index 2 that we see here, and it has its stable and unstable manifold. Try to represent in these black lines here, and in between we have these index 3 orbits, and we have a family of planes. So we have these 2 index 3 orbits. So it's the same here, and a family of planes asymptotic to each index 3 orbits. In fact, one family, 2 families of planes. And we have cylinders connecting. This is the index 2 orbits, the same, connecting them. So this is essentially what's happening with the dynamics for when you increase a little bit the energy for the first interval of high energy, for small high energy. So we have the situation here. So that's that foliation that I projects as a foliation in these 2 planes, like I'm showing here. So this is the Lyapunov orbit in the neck region. In the other plane, we see it rotating like that. This is the index 3 orbit that we see in between the Lyapunov orbits. And it's rotating here in this plane like that. And this is the cylinder connecting the index 3 to the index 2. It's given in green, and it projects in between these 2 curves here. And we have these 2 regions here, which in this foliation means like one of the regions is here and the other region is this other part of the region. So we have a very simple description of this flow in these higher energy levels, given by this foliation in this first interval. So how we obtain these holomorphic curves? Because in this, we are not so interested in studying the dynamics of this system, because the dynamics is quite simple. We are just interested in studying the existence of these holomorphic curves to push later to other systems, such as the trivariate form. So because of the symmetry of the system, here we can use, let me just give an idea. We can use action angle coordinates here. And so we change coordinates such that this Hamiltonian, which is this part here, it becomes simpler after you change coordinates. And then we can more or less solve explicitly those planes that we see. We can use this extra symmetry of the action angle coordinates to solve more or less explicitly the PDE, pseudomorphic curves. And in fact, it's essentially explicit, meaning instead of solving a PDE, we translate this problem into solving an ODE. It's a very simple ODE. It's a one-dimensional ODE. So then we obtain this holomorphic for some of the leaves that we see here. In fact, we solve this guy here. We solve the green ones, and we also solve this purple curves. Okay, so that's the main idea. We produce these holomorphic curves, and then because you have this implicit function theorem, these holomorphic curves, they lie in finite dimensional manifolds, and then we use a compactness theorem to prove that these one-dimensional foliations, for instance, for those planes that we see in the upper part, these red planes here, they will foliate the remain all the rest of these energy levels, and so we obtain this foliation for this range of parameters. So when we increase a little bit more the energy, which is in this second range of high energy, what we see now in this plane, so the dynamics of K2 here is it has a bifurcation here. So instead of having just a center, now it becomes hyperbolic, and you have these two centers. It's a very simple bifurcation. So the dynamics change. And it's not possible to use action angle coordinates anymore to produce the holomorphic curve. So we still need to obtain these pseudo-holomorphic curves to solve this problem. But now again, it comes the power of these curves. We can deform using an implicit function theorem, but a parameterized version of the implicit function theorem, where you increase the energy and the curves deform. And still, using a compactness theorem for such curves, we can show that this foliation persists, meaning that the foliation that we saw in the previous case remains the same. So we still have this type of foliation. It's like you have these two spheres, one inside the other. We have these families of planes bounded by index 3 orbits. We have these cylinders connecting the index 3 to the index 2 orbits. And the flow is it's very simple. It's transverse to these leaves. And in fact, the flow here is integral. It's very simple. It's the flow more or less does something like that. The invariant tori that you see is something like that. Okay, these are the stable and unstable manifolds of these orbits and so on. Okay, the flow is very simple here. So what changes? The first thing that changed is that
Pedro,
now,
are you I'm not sure if you're finishing because your time is kind of over, but you can finish
three
in 1
minutes.
minute. Yeah, it's fine, thank you.
Okay, so the last range of energy, so I'm not talking about the symbolic dynamics, so instead of having this bifurcation that occurs in the transverse direction, there is a bifurcation which occurs for the leaves. Now, in this case, this region becomes smaller and smaller, and one collapses to the other. And what happens in the end, which is the expected picture, is that now we have just one component in between these two spheres, and the flow is even simpler than the previous one for higher energies when we start to see the planet. So the transverse foliation is like that. Instead of having these two regions of families of planes, we have just one region. And finally, just to mention that there is we can take the rigid leaves of these transverse foliations, like the purple and the green ones, and construct a symbolic dynamics. Every time the trajectory crosses these leaves, we associate like a symbol, like 1 or 2, and in this case, for higher energies, we have a symbolic dynamics with only 2 symbols, and in this case, the symbol 2 is when it crosses this purple region here, and the symbol 1 is when it crosses the cylinder, the green cylinder, which projects in the original coordinates here, and crossing meaning that the trajectory is tangent at some point, then it becomes transverse, these green leaves, and when it becomes tangent, it's a crossing point, it becomes this number 1. And what we see in this dynamics is just like the symbol 1 for the satellites, and the landscape is only 2 that we obtain here, and satellites we only see 1, and the planets we also have here, and it's also always 2. So this was essentially the main construction of transverse foliation for the Euler problem. Thank you.
Thank you, Pedro. Are there any questions or comments?
Pedro, in this
I have
last slide, sorry.
Yeah.
Yeah, I
Is there anybody speaking?
So you
sorry,
can
yes,
say,
I
you
wanted
can,
to ask a question, but I can ask later. You can ask first.
okay, Ali, please.
So Pedro, in this last slide, when you talk about symbolic dynamics, so I remember this restricted three-body problem also, that sometimes I have seen this symbolic. So here, how this, first of all, do you have all of the symbols, all of the sequences appear? As you said, you mean full shift. Everything can be realized. Is it?
Only the symbols here.
Yeah, yes, I know.
You mean in the three-body problem?
No, here, I mean, you have satellites correspond to 1, 1, 1, 1, but you can have this kind of 1, 1, 2, 2, 1, 2, etc.
No. It's only the symbols. Only the symbols. Only the sequences. It's a subshift. Huh?
No, this is just 3 points. So satellite, lemniscate, and planet corresponds to 3 points in the symbolic space, in the shifted space.
Yeah.
So,
But
I'm asking you if you have all of the symbols. I mean,
yeah, I understood. You only have this. This is the point. It's very simple, the dynamics.
Okay.
You cannot have like 1, 1, 2, 1, 1. You only have this, these sequences. Only two sequences for the symbolic dynamics. In the previous case, it's a bit more complicated, but in this case, you only see, if it crosses. So the point here, so to explain why we just have one, it's if it crosses this, this purple, then it will return to the purple, so it will cross forever, and it will never be tangent to the green, to one of the green curves. It's never tangent. Okay, so it's always 2, 2, 2, 2. So there are other orbits, in fact, the satellite, that they go around only the heavier primary, and at some point here, I don't know if you see, this, it's tangent.
Okay.
It gives a crossing of the green leaf. And then it becomes transverse, and then it crosses again. I don't know, but maybe a different point. And then, but it will never reach this this purple curve. So it's always 1, 1, 1, 1. Okay? So you only see it's a very simple symbolic dynamics. Here it's very far from being a full shift. It's only this. In the previous cases, we could see something a bit more complicated. So it's so the point here is that this type of foliation, I think it was never considered. This type of symbolic dynamics, and this is exactly what comes when you study these flows from a symplectic dynamics perspective. This is the symbolic dynamics that show up.
Well,
it's very simple, I agree, but it's something.
Ulysses, please.
Yes, I have a question that I think is not very smart. Maybe it's a little.
Maybe you should speak louder because, yeah.
Yeah, sure. But I was wondering if there is some additional tool that allows you to differentiate between like in the last slide, for example, to differentiate between the purple tool and the red tool. I mean, if you have some additional information about energy, I suppose you know which of the two situations you are encoding, but is there any intrinsic way to differentiate lemniscates from planets, for example? Is that like
in this picture, which is the intermediate range of energy, so you still have the Lyapunov orbit here, which is the hyperbolic one, And you still have this region that we see in between the collision orbit, the red one here. And what we see when we start to increase the energy, this Lyapunov orbit, it starts to collapse here. So that region that starts to disappear is related to this guy here. So there are some orbits here that are satellites that are doing something like that they will disappear. Satellites near the light primary, because this guy is the light primary.
Mm-hmm.
So what's happening is that this orbit is collapsing here. And then when you cross and the foliation is you know, these orbits, they are important part of the foliation, and now you have this strong transition from one type of foliation to the other, and the dynamics is different. Okay, that's what we observe. So I don't know exactly what type of you know, difference that you would like to see besides this type of collapsing behavior.
No, yes, that's it. Like, for example, if you perturb the energy of someone who is in the purple line, you'll see the other kinds of orbits, but this doesn't happen in the red line, right? Because this purple line was obtained by coalescing the hyperbolic lines.
Yeah,
so
that's correct. This picture occurs for every energy in that range.
Okay.
So yeah, it's for every energy. So you always see this picture here. There is no. So what you see here are satellites around the left orbit, or around the left primary, which is the heavy primary, and you don't see satellites to the right.
Okay.
But you see these planets, and the planets you could see before, even before in the previous case you could still see planets here. You had these orbits here.
So Yuri, oh, sorry, Yuri, do you want to ask your question?
Yes. Hi, Pedro.
Hi, Yuri.
So, am I mistaken, or is there some relation? I read it fast in one of the slides between the pseudo-holomorphic curves and finding periodic orbits.
Yeah, exactly. Yeah, maybe why using transverse foliations is this, or why using holomorphic curves?
Holomorphic curves, yes.
Yeah. You can. So the idea here is so now we have this foliation for the Euler problem because it's integral we can construct. So for instance, the three-body problem or the Hughes lunar problem and some other different types of deformations of these Hamiltonians, we can try to push these holomorphic curves to produce foliations for these other systems which are far from integral. Okay?
But why they persist? That's something, because it's like a perturbative argument. But I understand that if you use a perturbative argument, it's going to work just for parameters close to the integrable one, right?
Yeah, but it's not exactly. It's a cobordism. Let me try to quickly explain. You have this contact form, which is a model, which is like, let's say, the Euler problem, and you interpolate this is R, this is M, and this you interpolate the contact form of the model with your contact form, let's say, of a far from integral system, and then you have these holomorphic curves. These holomorphic curves, this is called a cobordism, symplectic cobordism, and your holomorphic curve that solves your model let's say a plane, it will also solve the J adapted to the coordinates. And because it's a family of planes that appear, in this case, in a two-dimensional, let's say two-dimensional family of planes, it is possible in this construction to deform this family of planes in the model, and then it starts to enter this transition region in between your contact form and the model, and you push down the family of curves, solving this interpolation problem, and you push to minus infinity. This would be the construction that in the end you have in the simplification of lambda a different plane that solves the equation adapted to lambda, and this will give like one possible leaf of your solution. So it's not perturbative. If so, Poincaré used a perturbative argument. So it doesn't work because you start to produce, you have the periodic orbit. The periodic orbit is non-degenerate, so it's preserved. The leaf is, it's transverse to the flow, so it's still preserved. The perturbations is still transverse to the flow, and so it's a perturbative argument. This is not a perturbative argument. You push the holomorphic curves down, and to solve if you are able to do this, and this is the method, to produce a holomorphic curve for your given contact form, and then you find a periodic orbit here, let's say P3, tilde, which has nothing to do with this periodic orbit associated to your model. It finds the holomorphic curve, since it has finite energy, it finds another periodic orbit, and it also gives you the, let's say, a plane, and you try to do it with the whole foliation. So that's one of the strengths of this method. It's not perturbative.
I see. Are there any other question or comment? If not, let's thank Pedro again for the wonderful talk.
Thanks.